Hello students, so today in this lecture we will discuss about super hydrophobic wearable sensors. Now, from now this hydrophobic, the word hydrophobic means phobia from waters. That is, it is water repellent. The opposite of this is hydrophilic. Now, to differentiate or categorize technically what does this hydrophobic or hydrophilic surfaces mean, we perform the following test. Suppose we have a solid surface on which we provide a liquid droplet on a solid surface. Now, in this case, there are three interfaces formed. The first one is between the solid and the liquid. So there will exist a surface tension between the solid and the liquid state. So let us call this state so this is the liquid state, and this one here is the solid state S, and this is L. So the surface tension between the solid and the liquid is gamma SL or LS. Similar to that, we will have surface tension existing between the gas. This is considered to be the gaseous state or vapor. So there will be sigma Sg, and this point is where there will be the surface tension between the liquid and the gaseous state. Okay, now let us draw this once more. Now this angle that the gamma Lg makes with the solid surface, this is called the contact angle. Okay. Now usually if the contact angle is more than 90 degrees, then it is called hydrophobic. And if it is less than 90 degree, then it is called hydrophilic. However, if this 90 degree range if it moves to greater than, so the hydrophobic range exists not only greater than 90 degree but 90 to say 150 degrees centigrade, 150 degrees centigrade. Okay. Now if somehow this value it exceeds uh, it exceeds 150 degrees, then we actually call it a super hydrophobic. And similar to this, if this value is less than 10 degrees, then we call it as super hydrophilic. Now there are three different models based upon this hydrophilic and hydrophobic properties. The models are, first one is the Young's model. The second one is the Wenzel's model. And the third one is the Cassie-Baxter model. Okay. Now the Young's model is simply it says that the cos of the contact angle is equal to the difference between the surface tension at the solid gas interface minus the surface tension between the solid liquid interface divided by the liquid gas interface. Okay. So we will denote this contact angle by sigma theta y, that is due to the Young's model. And as previously told, if these are the conditions which are also satisfied by the Young's model. Now the Wenzel model introduces the concept of roughness of the surface into this model. So according to Wenzel's model, cos theta is equal to cos theta Wenzel is equal to the roughness factor into cos theta Young's. Now this R is simply the contact area, real contact area divided by the apparent contact area. Now the difference between the real and the apparent contact area is usually due to the fact that in this model, if say we are assuming that the surface is not smooth but it is rough, so water droplet which falls on the surface will have different contact areas and due to the roughness. And usually this roughness, if it is more than one, it means that the real contact area is more than the apparent contact area. Now, this roughness can be already present on the surface or can be due to the microstructures which get absorbed on the surface. So from the equation we can see that we can say that the contact angle due to resistor, if it goes less than 90 degrees, then we are moving towards the hydrophilic nature. However, the contact angle due to Young's, if it goes more than 90 degrees, then we are going towards the hydrophobic nature. Now, the third model, that is the Cassie-Wexter model, it is based upon the concept that although the solid surface has a roughness, uh, the liquid surface is with this one, this is not completely filled with the microstructure. So there are places where there is a gap, and that is gap is actually the liquid gas surface. So the liquid solid surface, LS surface, is separated from the solid surface by air, in the solid surface. So if this is the case, then we will assume that there is a barrier between the roughness created and the so this would be L and the liquid droplet. So if we consider the contact angle due to the Cassie Wexter model, then that contact angle, if put in this equation, let us CB is equal to, mathematically is equal to F1 cos theta y due to Young's minus F2. Where F1 and F2, the F is stands for the proportional contact, and F1 then is for the solid liquid surface, and F2 is for the gas liquid surface. A gas solid surface. So what can be derived from this relation is that the contact angle due to Cassie-Wexter model is proportional, that is inversely proportional to 1 by F1. That is, more is the contact area, solid and liquid contact area, the less will be the contact angle. However, it is proportional to the roughness of the sample. Okay, so these are the three different models for the super hydrophobic surfaces. Now, this super hydrophobic surface are used in making wearable sensors. Wearable sensors are those sensors which are in contact with the body, and they are used for the detection. They detects the motion of the body, or the changes that is taking place inside the body by like motion or limb movement for that instance. Then the pulse, the blood pressure, and voice, then breath, and so on and so forth. So these detection of these motions or changes in the body are associated with sensing the strain or any sort of pressure, then detecting gas, detecting frequency, and to some extent the temperature. So these are the things that usually change with these actions. And the sensors are the variable sensors are mainly designed to detect these changes. Now, why the necessity of super hydrophobic material comes into the picture? The reason is that the body it while changing its position, it releases, it can sweat, or there can be other hindrances, environmental changes like absorption, humidity, temperature, which may change the surface of the sensor or the substrate on which the sensors are mounted. Now, if you are making the surface super hydrophobic, then these changes will not affect the property or the efficiency of the device. So that's why SHPSO based flexible substrates are used. And the substrates usually that are used in making SHPSO based wearable sensors are PDMS, PU. PDMS stands for polydimethyl siloxane, then polyurethane, then we can have the rubber as a substrate, then any fabric, textile, and then miscellaneous materials like carbon black, natural latex, polyvinyl fluoride, PUDS, and etc. Okay. So by making these materials, we make sure that the environmental changes or any changes occurring in the human body does not affect the properties of the wearable sensors. Just give for example, this PDMS is used in making bio sweat resistant wearable sensors. It's called bio sweat resistant wearable sensors, and wearable, in fact, wearable tribo electric nano generators. Now, the design of this triboelectric nano generator is have gold along with elastic resin and PDMS. So this gold is for the conduction. However, this elastic resin and this PDMS, they are incorporated with carbon nanotubes. So this carbon nanotube, which may be engraved using a CO2 laser. Now these carbon nanotubes, they are the reason that these materials are feasible, even are become super hydrophobic, and are feasible even after a huge changes that takes place between them. For example, a 200% strain or any sort of chemical change on the surface, even if they are facing these sort of changes, there is the, the sensing property of these sensors remain the same, or not that much affected. And so this is the gold. Through which the conduction is taking place, and you have elastomers, elastomer, and then again there is PDMS, which has been coated with carbon nanotubes. So due to this, there is a conduction which takes place between the two electrodes. And it acts as a sensing device. Similarly, a structure where you have both super hydrophilic as well as super hydrophobic materials. Now, these sort of devices are usually used to collect sweat and to analyze. Now, what this super hydrophobic, the walls, what will do, it will make sure that the sweat that is getting collected, they are in a proper channel. They are not dispersed here and there. And what this super hydrophilic section, which is inside the super hydrophobic, they will cause a high capillary action for fast movement of the sweat sample that is being collected. So this super hydrophilic and super hydrophobic materials also can be used to be working in tandem.